where it just started to be eerily human-like in some ways. Obviously, it's not human at this point, but it has some human-like qualities. And so this has clearly diverted an enormous amount of attention, funding, research, and effort to those kinds of models. And so we're going to be, seeing more investment in that direction, obviously, in the near future. But with the thing about AI and science in general and technology in general is that there's always going to be surprises. So it doesn't just mean it's a straight shot of larger and larger language models, like from here to AGI or something like that. I would expect surprises still to be coming. But we've certainly learned some lessons about size and data and scale that will probably continue to apply even as architectures perhaps surprise us and shift.
Mm-hmm. Yeah. So, Dr. Jiang, obviously the theme of this conference is.
You can always refer me as Hong Jiang. That's maybe easier.
Okay, Hong Jiang. Okay.
Right.
I'm trying to pronounce the surname properly, but Hong Jiang, thank you.
Doctor just make it too official.
Okay. Well, thank you. Well, so obviously, it's understandable that the theme of the conference is large language models, and it's just such an exciting time. For someone who covers AI, I've never seen anything like it. So, but I would love to hear your perspective and how you're thinking about it as the chairman of the BAAI.
Well, the acoustic here is not that good. So could you repeat the question one more time?
Yeah. Okay. Sorry. So what I was asking was, given that we're experiencing a big moment in AI,
right,
what do you think, in the big picture, it means for the status of AI research and the direction maybe that you'll be taking at the institute?
Well, it's definitely a big breakthrough that make every one of us who has been working in the field to rethink the approaches we have been using and the system architectures we have been building and the algorithms we have been working on. Before ChatGPT, there are tons of effort looking at various algorithms. But I have always been a big fan of a system approach, meaning that AI technology, AI itself is going to be a system, and it's not just a single algorithm. That's actually, one of the reasons why I it's dear to me. This particular forum, this particular discussion, and also Ken, your book on success cannot be planned. But if you look at what we have been doing, and in most of the computer science field, we tend, especially in academia, we tend to look at a single algorithm and try to improve it bit by bit. But OpenAI took a totally system approach, and especially if you think about the transformer was invented by Google researchers, and they have came out of many, quite successful models, but none of them really has ability of emergent. And has shown the power of ChatGPT and has so brilliantly combined the data alignment, algorithm, and infer together that led us to this breakthrough. So I think the entire field is rethinking, how we carry on research, what is a right or most appropriate, most effective approaches to approaching this, approaching AI problems, and give you an example in the natural language processing field, which is a very fundamental sub area in AI. When ChatGPT came out, at least I know among the top groups in Chinese universities, they basically tell themselves, now we need to look back They actually, one of the university really told the students, PhD students, say, if you graduate this year, we can't stop you because you have to graduate. But if you graduate next year, you need to rethink your thesis, because what the problem you're trying to address already, to a large extent, solved by GPT models. So
yeah.
So, although you could still graduate if you continue along the direction, but really your work is meaningless. I mean, in terms of adding to the state of art.
Yeah, that's pretty extraordinary. I was at an event here at MIT recently where they had some linguists and cognitive scientists who were also saying that GPT-4 and these large language models was changing their fields, changing other areas of science. Well, I guess, Kenneth, on the subject of what might be missing, you mean it's interesting? Is there anything about what we've seen with especially ChatGPT that makes you think here is a really exciting new direction? I mean, I think Hongjiang alluded to some of the things there. Yeah, I'm curious what you think.
But yeah, when we think about what might be missing in exciting new directions, I mean, there's exciting new directions that build upon it and that now we can have opened up that weren't possible before. And then there are limitations, of course, where it's like these are problems that still exist in the models. So let's see, so maybe to start with just exciting directions that just build upon what we have. One is, I think, that this is a very unusual one, which I don't usually hear mentioned, but I think about it a lot, which is that we haven't had the ability of a computer to actually grapple with the question of what's interesting before. If you just think even back 2 years or 3 years, you could never imagine from a subjective point of view to even begin to say, look at this idea and tell me what you think. Like, is this actually a good idea? Could this lead in a good direction? And for the first time, actually, you can have the computer begin to grapple with this kind of subjective question. And if you think about it, this is an extremely important question. What is interesting and what is not interesting, even though it's totally subjective, because it's the seed from which all research and innovation grows. It's like I decide what to do based on what I think is interesting. And so if these kinds of models are someday going to actually solve like big, momentous problems in our world, they need to think about which directions are the most interesting to pursue so that those will become stepping stones to actually solving these problems. And interestingness is a separate issue from whether you're solving a problem. It's just a question, was this an interesting research idea or an interesting piece of art or an interesting story? And it's very intriguing that suddenly it actually can start to engage with that question. And not just in the sense of giving you a rating, it can even give you an articulate analysis of why something is interesting. And this is the beginning of innovation. It's like the beginning of autonomous innovation. So I think that's super interesting that that's now possible. I could also talk a little bit about what I think are interesting limitations, but I'm not sure if you want to go in that direction already or not.
Well, no, actually, why don't we, Hongjiang, what do you think of this idea of algorithms identifying what's interesting and maybe being a kind of innovation? Does that sound like a promising concept to you?
Definitely it is, although my own expertise are not necessary in this area. And definitely I think this is very promising direction.
Yeah, it's I wonder though, Kenneth, do you think that there's real can tell you something that's interesting that a person can't tell? Do you know what I mean? Because sometimes when you see ChatGPT, it is impressive, but it doesn't seem that original. So do you see examples where it finds something interesting that maybe no person would?
Good question. Yeah, I believe that there's some serious limitations when it comes to comparing to a human's instinct for interestingness. Yeah, these models don't come close. That's true. So it's just the beginning of a glimmering of the ability to grapple with this question of what's interesting. But that's still extremely useful, because it's like it always comes up in sort of whenever you're thinking, what should I do next? And if you want something on its own to think about, what am I going to do next now that I finished this task? And what's the next thing that would be interesting? It's got to think about it a little. And even being able to do it a little bit is still really intriguing, but it's obviously something we need to build on. And in fact, when you talk about like unoriginal, that's totally true. They're not good at being original. That's one of those really interesting limitations that I think is going to require improving the models. And I would just point out that being original is related to being novel. So novelty comes up. And there's a problem, I think, with the current paradigm with being able to identify novelty in a genuine way. Because if you think about it, novelty is a function of chronology. It depends on the order in which events happened, whether an idea that you have now is novel or not. But if you think about it, the model is exposed to all of history simultaneously. It doesn't experience its training data as a chronology that happens in an order. And therefore, it's not actually experiencing that, moment of epiphany when you say, oh, this is really interesting because I've never seen anything like that before. So if in the data, for example, it says something like, that's a really novel idea, it's not in the context of what came before. It's in the context of what came before and what came after. So it's very different from the way that we experience novelty. And because of that, novelty is really not in the data in any substantive way. And that means that I would expect it not to be good at thinking about novelty, generating novelty, and so forth. And to solve that will require, I think, somewhat of a paradigm shift because you've got to deal with chronology.
That's so fascinating. I was talking earlier this week with Demis DeepMind, and he was saying, I was thinking of this, Hongjiang, because you mentioned alignment and some of the technologies that went into ChatGPT, and he was talking about reinforcement learning being very important. And obviously, one of the things with AlphaZero and AlphaGo was that it could come up with completely novel sort of strategies. And it's not, it's very different from a language model, but it's interesting, like things that people could never come up with. I mean, but I wonder if one of the you mentioned alignment. I wonder, Hongjiang, if the reinforcement learning or other types of machine learning are of interest to the Institute, to you, as a way to kind of broaden capabilities.
Definitely. Actually, reinforcement learning and alignment they are in AI and in the building big models. They are not two different things.
Right.
Actually, reinforcement learning is used in alignment process. In the learning process, that's exactly what made ChatGPT, what made GPT-4 much better than GPT-3. The very development from GPT 3.0 to instruct GPT and then to ChatGPT is really the alignment process that used reinforcement learning. That you use human dialogue data, you use human feedbacks, and through reinforcement learning to get the alignment. So it is a super important learning algorithm. I mean the reinforcement learning in the alignment process, and alignment is a very critical step or approach to AGI, to large models safety and human aligned to human values. So it is super important. And also alignment itself is one very effective way to refine and train the model to specific applications.
Right.
You fit more domain-specific data into the model through alignment process. That will help us to really adapt the model to various scenarios, various applications, various verticals.
That's great. And are there other techniques that you're interested in, or you think? I mean, I know there's the Wudao model, which is, I think, my understanding is it's somewhat different from some of the other ones. It was multimodal to begin with, right? Are you looking at other techniques from machine learning anywhere that, like, what are you interested in for the next generation of these language models?
Definitely, they are. We before ChatGPT or before GPT-4, people in the field have been working on various models, and like Google Brain came out of BERT, like before that GAN, and all those the studies and researches have contributed to the field of large models. And although today we see the pre-training that based on transformer and combined with alignment, is the most efficient, effective approach that led to GPT-4 and led to many models who try to repeat the success of GPT-4. But we do see there are a large space. There are many issues that still have not been solved that would require further study and further research, and that calls for new algorithms, even new architecture too. So you also mentioned a multi-modality model. Definitely, that's one direction people in the field are pursuing very hard, and we do see that is the future direction, if not the ultimate direction of AI models. We human perceive information, perceive knowledge through a multi-modality. We read, we learn from language, but we also watch movies, we watch video, we look at pictures. So the way we acquire information is multi-modality. And so I'm not a neuroscientist, but I believe our thinking in our brain is also multi-modality. Right. So there is no reason that our AI model is the only language model. But I want to emphasize language model is the baseline, is the platform. And it's not only it is true that we learn how to build models through building language models. We the technology we learned, the know-how we learned, the insight we learned from this will help us to develop the multimodality model. Actually, multimodality model could be simply is a continuation of a language model. So the good thing about using a transformer is basic architecture. Here is every modality, data in every modality for to transformer is just a sequence of data. Text, language is a sequence, and image, if you scan the image into through patches, is also a sequence. And video is a sequence, and music is a sequence. So it can host all those information and embedded them into the learning, pre-training structure and train the model itself. So if we believe the future will be the autonomous intelligence, meaning that the model itself can reason and understand and plan and take actions. The model itself got to be multi-modality, and definitely if you want to apply it into robotics, autonomous robotics in the future, and general purpose autonomous robotics, definitely it will be a multi-modality model.
Well, that's a great segue to Ken, your work on sort of open-ended learning, continual learning, and that the point you made just a moment ago about temporal data, it shows that maybe the ways there are more dimensions by which we're not approaching intelligence. Is that fair to say? I mean, I guess, how do you think of this multimodality and other ways of building intelligent systems, and do you think that requires completely different architectures and approaches?
Yeah, I mean, I think a lot because these models are so powerful. It's just intriguing for me from the point of view of a researcher to think about what is missing. That's what I think a lot about. What is still missing? Like what kind of fundamental things are missing? And there's not a lot of things that are very, very clearly missing. Because you could say, well, it's just as long as I have it in the data, it's there somewhere. It'll get eventually picked up. So we have a big advantage with the amount of data that we have. But there are these, very specific kinds of things where it's not just intrinsically in the data because the way the data is presented. And one of those is this chronology. Like chronology is not in the data because the data is not presented chronologically. And another one that's like that is multimodality. Of course, like multimodality is not in data, which is only text. So that's clearly an opportunity. So, we're going to see no doubt advances with multimodality. Chronology is a little different though, because you can't just like put it in. It's not clear what that means exactly. It's not, you can't just put in chronological data into something that doesn't process things chronologically. And like part of what there is a little place you can sneak in chronology in these models, which is in the context itself or the prompt. Like that's a place where it can have an order. But the thing is, like all of human history generally won't fit in the current kinds of prompt space and probably won't for a long time. And so that's for all of the internet for that matter. So that's a problem, which is just an interesting research problem. So I think there's just a few of these things like chronology and multimodality that you can point to concretely. And then others are more like a wishy-washy, like hallucination, where it's like we see problems, but we don't really know, we can't really point to exactly the thing that's missing. What is the thing that's the problem there? Sometimes I've thought that maybe with hallucination, the problem is that it's a nonverbal activity in order to understand what you actually know and don't know, which would mean it wouldn't be in the data. Like what the reasoning process I go through to think about, do I actually remember this thing? Like when I'm inside my head and not actually articulating this outside my head, but just trying to remember something someone's asking me. There's some reasoning process where I come to a conclusion, I don't actually know that, or I do know that. Maybe if it's nonverbal, then it's not in the data because the data is just what came out of your mouth, not was, before implicitly in your mind before that. And so maybe there's something missing there, perhaps, but it's a little more amorphous to point to. But it's just a general interesting exercise, I think, to think about what's missing, still places that we can press forward.
That makes me think maybe there's some important insights to glean from cognitive science. So if you think about, experiments that will show the way people think or reason, sometimes it's not verbal or not text. Do you think that that's an important approach? Just to continue what you were saying.
Maybe. I mean, I think historically that hasn't panned out that well. Like if you look at large language models and the successful side of where they are, which is quite remarkable, most of it is not as a consequence of, looking at cognitive science experiments, and perhaps to the chagrin of cognitive scientists. And so, but that doesn't mean that it can't be helpful going forward. But I would imagine it's mostly helpful more as just inspiration, because the very implicit nonverbal reasoning, even if it exists, is just so inaccessible. I would expect it more to be something that would be emergent from the right kind of training than something that you could extract explicitly and then sort of write down like this is how it works. So it's more. I'm imagining we would more want to reorganize training in some way, maybe through reinforcement learning or something like that, so that we can elicit these kinds of steps that are nonverbal, which correlate to what we do when we're trying to determine if something is true or memorable or something we remember or do not remember.
Hongjiang, do you have? I think you have neuroscientists and cognitive scientists at the institute. What do you think we can learn from those fields? I mean, it's a strange time because it feels like language models solve so much, but yeah, maybe there are still things you think.
We definitely think we can learn from that from those fields, but it is still research undergoing, and it's still a lot of work to do. To be honest, at this moment, we haven't come to any significant conclusion we can apply them to building big models. But on the other hand, in contrast, Yeah, actually, I don't know if you read the recent work published by OpenAI folks using GPT-4 to analyze GPT-2 to the point that what's the function of the neuron in GPT-2, does when the GPT-2 generate a particular context, particular text or output. So that is very, very interesting. So I actually encourage those who working on neuroscience try to borrow some ideas from here. It's not just we borrow ideas from neuroscientists, right. But the other way around is also a very interesting research direction. But coming back to your initial question, yes, so BAI we have a extended group of scientists from Tsinghua University and from other universities in Beijing. We precisely looking at the problem of learning from neuroscience. We also have a small team building what we call life models, a simulation of human organs and simulation of brains. So to help neuroscientists to study, if a particular neuron is got activated, what's the how the entire brain react to it. So we actually have a small team working on that. We actually report to the in the conference yesterday on the progress.
Oh wow.
There. Yeah,
that's very cool. Well, talking about the brain, the complexity of the brain brings me to another subject, which is the size of these models, the amount of computer power required, and it's extraordinary, right? And I think we all know that, and that's one of the reasons why we're seeing such amazing results. But Hongjiang, to stay with you, what do you think that means for research? Does it mean that it's going to become less accessible, less possible for as many people to work on these models? Do you think we'll see maybe more efforts to make smaller ones? What does the size of those models and the amount of data sort of tell you about the future directions?
Yeah. You actually raised quite a number of questions. So one very straightforward one I would like to address is you mentioned about the researchers in academia. How would they react to this? Because anything to do with a big model require a large amount of computing power, and that simply require them to work on system and collaborate together, and collaborate among them, and collaborate among with their industry partners. And my experience with Tsinghua University, is that if you count how many professors or researchers in Tsinghua University working on topics related to big model, there are many of them. They actually have quite a high number of GPUs, but they scattered among different groups, right? So get them together, put their resources together is obvious a solution for if they want to work on bigger problems. But also I would say scientists or academians, especially those in the university, they should and they tend to work on basic issues, basic problems. That much of that still can be researched on without huge amount of computing power. But if they want to build the systems, definitely they need to collaborate among themselves and collaborate with industry. But one thing I would look at this problem with a positive from a positive angle is that actually I think the breakthrough of GPT-4 made many of us in the research community and especially in academia rethink what is the best way to conduct research in computer science in AI. And if we want to build a system, if we believe AI is a system and the problem can only be solved by system approach, then we should pull our effort together. We should pull our resources together, and we should, really form the research problems into something that we can work together on.
Mm-hmm. Yeah, I think you've done some impressive work in bringing together academics and industry so far. And
that requires a lot of effort. That's really requires a lot of effort. Yeah.
Well, what is the most challenging thing about that?
Well, I think I would first say that GPT-4's success actually helped us a lot. So from now on, I think it's much easier. But 2 years ago, it was much harder. Because a fundamental characteristic in academia is freedom, right?
Mm-hmm.
Professors get to work on whatever they are interested in. And this is a good thing about academia. But when we want to put everybody together from academia to work on one problem, and they tend to first of all, they naturally look at the problem from different angles. I'll do this part, I'll do that part, and but having them working on one thing, and or even try to segment a bigger problem into pieces, and I have each one of them work on one piece. It's just so hard. Because that's not how academia operate.
Right.
And but that's actually says a lot of why the first success come from open AI, because they take a system and the engineering approach. And then Google Brain, they have even bigger resource and a bigger team and a more well-known scientists, but they couldn't put the effort together to come up with one model. But they come with many models, and that's a showcase.
Yeah.
Academia in the universities, that will be the situation is much more fragmented. So that's really take require a lot of effort, conviction and capability to motivate people, and definitely capabilities to allocate the resources in the right way.
Yeah, well, that's great. And I'm Ken. I mean, you were at OpenAI. I'm guessing they had quite a lot of conviction around this singular sort of approach. But you've gone to academia. So what was your thinking? Why not stay at a place where you had huge amounts of resource?
You mean you're saying that I've gone to academia after? I was actually an academic before OpenAI.
Okay, but
so I actually went in the opposite direction.
Okay.
Yeah.
I see. So what was that what drew you in then, that you?
There's a long story, but it's a part of the story that I recognize that I'd have access to vastly greater resources. I mean, that certainly entered into my mind and is a big problem, I think, for academia, that pulls professors out of academia. They just can't provide the same resources. And I think it's a somewhat irreconcilable problem. I mean, it's not just it's not like you can just get full resources enough to match the unbelievable amount of industrial resources or money that we're thinking about in the future. Like, this may not be yet happening, but when you talk about things like systems that might cost $100 billion, I mean, that hasn't happened yet, but I don't know what academia can do about that if that does happen, like to match something like that. So it's a really interesting question, but you have to remember that hypotheses in science can be both related to scale and not related to scale. So there certainly are hypotheses that can be addressed even if there's $100 billion system sitting in some very wealthy company. But the ones related to scale, I don't know, like, we're talking about scale beyond imagination at that point. And it raised a lot of questions. But another thing to realize, though, is I think that's also interesting, is that even within these companies, they don't have infinite optionality. You know, if you're going to run, like, imagine you did have $100 billion experiment. It's not like you can try 15 different times and test all your hypotheses. And I mean, you're taking a bet and you're just going with it. And it's actually not very scientific. It's really based on gut, right? Because you can't really do the kind of systematic testing that as an academic, I really believed in. Like, that was what I was trained. You know, I'll try all the different parameterizations and I'll learn all the different angles on this and understand the system and how it works. Like, you can't afford to do that with a system like that. So it's not like they can just do all the experiments any academic would like to do. And even the researchers at these companies are very restricted in terms of like their individual hypotheses and whether those are ever going to get the light of day. So it's just like the scale is just unimaginable in the implications that it has. But I still do want to emphasize it's not a reason for anyone to give up, because I still think there are many hypotheses that can be worked out at small scale, and some of those can disrupt the larger scale. Like, for example, a major architectural revision. It's not like we go back to a neural network with 20 connections or some tiny thing. But, you know, like today's large model is tomorrow's old news. And so, like, the things that today take a lot of compute, like, you know, 5 years from now don't, and they're enough to test some pretty significant hypotheses. And so a lot of people will have access to that within a couple of years. And those hypotheses could reinvent everything in such a way that even the really big models need to be revamped. So I wouldn't at all give up because I don't have access to the most fancy thing. But it is an interesting dichotomy that's developing that didn't exist before.
Do you think there could be better sort of collaboration or cross-pollination? I mean, I'm sure you're right that in some ways it's irreconcilable, but it would seem that maybe industry could benefit from the perspectives of academics a lot, and they could benefit from the compute without completely, you know, derailing the academic sort of principles or you know, giving up all the secrets. But when you know, GPT-4, the paper has literally zero information, you kind of wonder if there are ways to maybe have more collaboration.
Yeah, I mean, historically there's been collaboration. It's not like there's never collaboration, but right. I think there's the cynical version and the optimistic version, like, and both are probably going to just play out at the same time, where some people are going to think, well, we can just read their papers, like, we don't need to work with them, or we can just hire them because we can just offer them 5 times their current salary. So why bother with all this? Like, there's a lot of complexity to, at least in the US, to collaborating with academics, because, you got to go through the Office of Research, and then there's all this legalistic stuff, like who owns what and where's the IP going. Some companies will just say, forget that, we'll just like hire the person out and you take them with us if we really care, or wait for their paper to come out. But then the optimistic version also exists, where it says, there is a lot to gain. And it's worth it to create this collaboration. And this person, I think the theory there is this person is actually more comfortable in an academic setting, more free. Like Anjan said, like, there's more freedom, which may be actually, in the interest of the commercial entity to have people collaborating that are more free to kind of explore just unusual directions. And maybe they want to encourage that to some extent because they do see it as in their interest. And so they go through the effort to actually make the collaboration work. And I think you're just going to see opinions vary, and both kinds of opinions will be expressed, maybe even in the same company sometimes. And we'll see a mix overall.
Yeah, well, I'm curious, when you Hongjiang, have you seen benefits from having academics help on or more involved, even though they're still within academia? I specifically, when there are problems with models, things like hallucinations and when people are worrying about alignment, it makes me wonder if actually there's going to be more good reason to have outsiders take a look at, or people who aren't, and more people have access to models.
I would say it's super important and critical to have researchers, to have academians involved in large model research. And you mentioned specifically alignment, but it's in all aspects of a large model research. The very fact is, today the model itself is still very costly. I'm just giving an example here. The model itself is very costly, not just in training but also in operating, in serving. running the model. So the training process is not necessarily the most efficient one either. And training model size could be optimized. So all those, if you kind of if we find a way to abstract those issues into problems that academians are best at it, and then it's the academians will find will perform and will make their contribution, and those contributions are critical. And so it's the matter is, we need people from academia to who are able to extract or abstract those problems, those issues, and work on them. So, for instance, we worked with a few visiting scientists from various universities on training optimization, so training efficiency. So you could say to speed up the training. Also working on model size optimization, and for the same performance, do we really need that model size? And also work on new architecture of models to make it modularized, right? Issues like that definitely require deeper research. Even on the building model itself, we do see the benefit of researchers from universities. Actually, they also feel beneficial as well, because otherwise they may not see that many research problems. And I think research is definitely about a solving problem, but research is also, to my extent, in my view, is actually more about funding problems, define problems, than just solve them.
Okay, Ken, you're nodding. Do you want to say anything more on that?
Yeah, I mean, I strongly agree with this point that academia is an essential and critical link in the chain. Like that ability of professors to explore with a different kind of freedom than exists in industry will expose opportunities that just won't happen in industry, and that's going to be essential to progress. So it's this is a vexing problem. I think that industry tends to, at the moment, suck people out of academia and hurt these departments and the entire academic enterprise. And like, it's worth a lot of thought, I think, from the university side, like how to counteract this, because from their point of view, it's unprecedented. Most fields, I mean, most academic fields don't have this kind of thing happening to them, where it's like just so much more lucrative and better just to go somewhere else. Most people don't have this kind of optionality. But in this field, it's very different. And so universities, I think, need to treat professors in this area differently so that we can maintain that fabric, which trains the next generation and exposes these ideas that are going to be essential that you're not going to get in industry. And so, yeah, both sides are totally important.
No, that's great. Those are great thoughts. Well, we've talked a lot about language models and ChatGPT, but we haven't brought up safety in the kind of the AGI existential safety. And it's, I mean, I wouldn't normally bring it up, but it's such a big topic of discussion. And it seems like a lot of people are taking both the short and the longer term risks seriously. So I guess, speaking about both the long and short-term risk, I want to just ask how that affects research. I mean, is that going to become a huge new, but it seems likely that it will, area of research? Will it affect disclosure? Will it? So, Ken, how do you think that this is going to change? And I don't know where you sit when you on the spectrum of worry about AGI and AI.
Yeah, no, I think it's worth worrying. But I mean, I guess where I sit is more of, I think somewhat of ambiguity. Like, I'm not totally sure how worried to be, but I think it's worth being worried. because there are a lot of things that could turn out to be very significant short-term and long-term threats. But a lot of people discuss this issue with certitude. And I think that at this point in time, that doesn't really make sense. And it makes it actually hard to disentangle like what we don't know from what we do know. And there's mostly what we don't know, I think.
Right.
Okay, so that said, though, I think that clearly it's a field, like, AI safety research. Already people say I'm an AI safety researcher, but I don't think it's a separate discipline, in the sense that like creating more intelligent machines is actually building AI safety. And this is a paradox that actually is very difficult to solve for the field, because you could think of it as sort of this simple dichotomy where there's safety research and then there's improving the model, and then you could say let's put the brakes on the models and just work on safety, and then we can make the models more powerful. But the problem is making the models more powerful could be what makes them safer. After all, sanity itself is like a really important aspect of safety, and sanity is a function of high level intelligence. And so this relates a little bit to like points that are made in my book, where we talk, or the book that I did with Joe Layman, where we talk about how, often the things that lead to what you want don't actually look like what you want. And so like if we just focus myopically on safety, and safety is safer and safer and safer, the problem is that the thing that really leads to a profound and fundamental shift in safety might not look like safety research right now. And so other kinds of research then needs to be happening, because that could be the stepping stone that leads to the real revolution in safety. And we don't know, because we don't know what the future is. So we have to keep our options open. And it leaves us in a very kind of awkward position, I think, because obviously at the same time as this kind of advance could lead to safer systems, it could also lead to more dangerous systems. It's like just as possible that getting really powerful is actually extremely dangerous. And so we're just walking a tightrope on this, and just have to, I think we should just acknowledge that we don't actually understand the parameters of the dimensions around us as we try to walk the safety tightrope. And we should just be very careful, obviously, moving forward because of that.
Wow, yeah, those are very great points. Hongjiang, how do you think about safety, long-term risk, and how does the Institute looking at short and long-term risk?
Yeah, just for your information, in this BI AI conference, yesterday morning, we in the opening keynote addressing, we have two scientists with a kind of opposite view. We have a Max Telemark from the Future Life Institute of MIT, and who actually initiated the petition to pause AGI research for 6 months. That definitely brought up the awareness of potential risk of AGI. And then you have Yang LeCun, who say, "Oh, we are far from AGI. We at this moment we still need to work on, get AI models more intelligent. We are far from AGI. GPT cannot understand the things at the level of human intelligence have." And so and also today we have a one-day session on safety and alignment, and we actually start this session with Sam Altman. Just this is 1 hour ago, addressing the audience, and he is in the world tour and really on this particular topic. So I then had a Q&A session with him along this topic, and I think Max did the right thing, and Sam did the right thing to bring up the awareness of the potential risk, and I really think he's doing our mankind a service by making these tours, by talking to various government, various institutions, and on our research side, BAI, when we I think 9 months after we established BAI, we actually joined forces with academia in China. We actually published this Beijing principle on AI ethics, and safety was definitely an issue there. I think also after the petition that Max initiated, we actually have quite a few Chinese scientists sign on that petition, including our very director of BAI, who running the BAI daily operation. He has signed that as well. He has been in the effort ever since Max had the first conference in 2017. And so when we looking at this issue of AGI, now we definitely spend a lot of time thinking about ASIC. That's for sure. Think about ASIC, and safety then come naturally after that. And we have team looking at data. We have team working on algorithm that clean up the data, and we definitely have more effort working on alignment. But I tend to agree with Yang Lacong a little bit more than Max on this, and that we are still far away from human level AGI. So we still need to spend a lot of time working on that. I like Kenny's point on smarter model actually could make it safer. But I definitely support, and BAI definitely support Max effort to bring up awareness, to set up consensus, and to mobilize the community to looking into the issue.
That's great. I'd heard that some scientists there had signed Max's pledge, and I'm wondering though, is in the US, in the West, I think this issue has become quite headline news. It's become a big story. Is it a big topic in China generally, would you say?
Definitely,
okay.
Definitely among the AI circle for sure, and on the media for sure, and then government agenda as well, as far as I can read from the media. Yeah, definitely. It's so that's why I said it's a good thing that Max and the community, put the effort to bring up the awareness on this particular issue.
Yeah, it's good. I mean, it's good to hear that, and I think that scientists are the ones who are going to probably have to take a leading role in that. I would imagine, right? Kenneth, I don't know if you have thoughts on this, but there's talk of regulation and how things would work internationally, and how countries that are very big in AI would ever figure things out. But do you think that there's a path to that scientists can kind of offer some ways to sort of align themselves, to use that word, around certain sort of principles or whatever?
I mean, this is a really big question. The way to organize, not just scientifically, but politically, in order to somehow route this giant oncoming thing into some good direction. I think, scientists, of course, play a role, but, one problem that we have to accept is that just because you understand the AI doesn't mean you understand its social implications. And there's another problem, which is that just because you work in, say, social sciences doesn't mean you understand the social implications of AI either. So we have a problem that there's not really anybody who's truly the right authority who can just tell us the ground truth here. It's what should we do? And this is leading to this, very ambiguous and confusing situation that we have when we talk about regulation, because there isn't an ultimate backstop of authority figures. It could just be oh, of course you should just talk to us. But we do have this sort of tendency to go to the AI scientists, which I think we have to be cautious about, because they're not necessarily experts on the social implications of the scientific insights they've had. And so, of course, though, their insight into what the technology does is important. So they obviously have to be part of the conversation. And so overall, though, it seems like where things are heading is towards, I think, probably regulation will most hit the larger models. And so, it won't be affecting smaller academic types of research that much, is my guess. But like at the highest level of power, I mean, Sam Altman has said similar things, that's where you'll probably see like a much more tight regulations, models that are actually threatening in some way to sort of human stability. And then it's interesting that that's sort of similar to the problem of not having access to the most powerful models to begin with for the academics. So it's sort of like almost like it doesn't even matter that much because they won't be able to do anything with those models anyway because they're too powerful and they don't have access to them. And so it's really going to be hitting in this kind of very refined circles, but it's very important nevertheless. It's extremely important because like these models are potentially dangerous. And so, I think it's a group effort to find some kind of amalgam of people that we feel we can trust. Because the biggest problem I have is that I don't know who to trust. I wouldn't even trust myself. And that's a big problem, to actually get a grip on this issue.
Well, no, those are great points. I think I want to finish on a upbeat, positive note, because obviously this is a really exciting moment in, once in a generation, I guess, for at least for AI. So we're pretty much out of time, but just briefly, Kenneth, what are you most excited about when it comes to the future of AI research?
Well, I think I'd say maybe just throw out two things. And one is just the amplification of human creativity. We're looking at a world where right now there are many things that you may want to do and have ideas about, but you cannot do because you don't have the skills and you don't have the talent. And this is about to change. And that's really interesting in terms of empowering human creativity that, I can't write the story that I have in my mind, or I can't paint the picture that I have in my mind. I can't build the robot that I have in my mind. But suddenly the facilitator can actually come between my ideas and the actual implementation and make all these things reality. And it's just hard to even imagine that world, where like it's like I have the germ of an idea for a song and it's suddenly like a fully produced, like radio quality song within 5 minutes. What is that going to be like? I think that's very empowering to people and has a lot of upside to it. And the other thing that I think we don't hear that as much is just maybe this can help us to do better at finding ways to interact with each other, finding ways to connect with each other that are more virtuous than, social media today, where obviously there's all kinds of issues with toxicity and so forth, and the ability of machines to maybe think a little more deeply about what we really need and what's healthy for us on our behalf at a huge scale, like billion people, might be able to help us in some way to connect better with each other, which I think would be a nice antidote to this thing that we're facing right now, is that a huge proportion of our time is going to be spent talking to a cold machine. And it'll be nice if it can actually help us to have more humans too.
That was a great point. Really good. Hongxiang, what are you excited about for the future?
I'm very much in agreement with Ken. I think after 60 or 70 years of research in AI, we finally come to the point that we realize AI can really empower people. Ken mentioned about empower people to create things on your mind, and I'm also very excited on finally we can have AI that can empower robot. Today's robot is so much specific task oriented. Can only do one thing. Inspect a component or pick up one thing and serving very, very, very specific task. But with the advancement in the big large language models, especially in future in multimodality models, we can see that will be completely rewritten. Even autonomous driving will be completely rewritten, and with the systems that have more autonomous ability, more planning ability. Today, even GPT-4 does not have those kind of capability, but as a scientist who has been working hard in the last 30 years and try to bring up something that we can convince people, oh yeah, finally the machines can do better, and finally the machine can complete the task, and it's very exciting. But I do want to quote Ken's book. A great success cannot be planned. So what we are doing now, and what I have been telling my funding agencies, when I raise money from government agencies, from industry, they often ask me a question, in 5 years, so what can you deliver? I always tell them that all I do is to increase the probability of success in AI. That will bring good things to the society, but I cannot promise you what exactly I can bring to came out of it. But it is a probability that I'm going to increase.
Thanks.
Okay, well that's a great note to end on, and a good ad for Ken's book as well. Well, I've really enjoyed this. Thank you very much. Thank you, Hongxiang, for hosting this, and thank you for being on it, and thank you, Ken, for joining us and being a guest here. It was an excellent discussion.
Well, thank you very much.
Really
For staying so late, and Ken, thank you for taking the time, and great to see you over Zoom. But hopefully we'll see each other in person, if not in Beijing, but maybe in San Francisco or Cambridge.
Sounds good.
Great.
All right, thank you. Bye.
Okay, take care.
好了，是吧？
好的，各位观众大家好，下一个环节的话，我们欢迎来自 Meta AI 的研究员，他同时的话也是模型 OPT 的一作，苏森张来进行一个线上的报告，报告题目叫做 Trials of Developing OPT 175 billion。那简单介绍一下我们的Susan 老师，他是毕业于普林斯顿大学数学系，一直专注于大规模AI 这个基础设施的那个设计，同时的话，他也是OPT 的作者，然后在模型以及软件系统研发方面有超过10年的一个经验。下面我们有请 Susan。Hi.
Hi, everyone. Yeah, thanks for having me. Should I just share screen directly?
Yes. You can start the presentation now.
Okay.
And after that, I'll gather some questions from online, and we'll have a short Q&A session after your talk.
Okay, I think I need to fix my setting. 1 second. Sorry.
我们可以放 PPT 了是吧？哦，它 share screen。你 share your screen 的 PowerPoint？
Yeah, I'm trying to. Oh, I have to restart. 1 second. Sorry.
Okay, no problem. 大家稍等片刻。
Okay.
PPT。
Can you see the screen? Is the screen good? Oh, hello.
Hey, everything's good now, Susan.
Okay.
We can start the speech.
Okay. All right. Hi, everyone. Thanks for having me. So today I'm talking about the trials of developing OPT 175 billion parameter model that we released last year back in May. So just a bit about me. So I studied math many years ago at Princeton University. Afterwards, I spent a significant portion of my career building these large-scale distributed systems to support data processing workloads. I then moved into building reinforcement learning systems at OpenAI from 2018 to 2020, mainly focused on the Dota 2 and OpenAI 5 project. Afterwards, I briefly moved into the hardware space for photonic chip design at Luminous Computing. When that didn't really work out, I moved back into AI software in 2021 to develop large language models at Meta. So this talk is mostly focused on the early parts of developing LLMs at Meta, specifically for the 175 billion parameter model we trained back in 2021. So the setup here is about a team of 5 engineers. We were tasked with training this model in just about 3 months using 1024 80 gig A100 GPUs. These were the latest generation of GPUs from NVIDIA at the time. And with the training efficiency code that we had, we still needed about 33 days of continuous training, assuming no hardware issues, no failures, nothing, in order to go through 300 billion tokens. We didn't really have an explicit infrastructure or systems team to support us outside of a customer support team from the cloud provider. And the data was kind of whatever we had available at the lab at the time. So this was a combination of a lot of the data sets that was used for Roberta and also for BlenderBot work from the dialogue agents team. For the hyperparameter settings, we were also familiar with a very different set of hyperparameters that were circulated with the FAIR NLP groups at the time. It was very different than the settings that was available or that we saw from Microsoft and NVIDIA for their Megatron Turing NLG work, along with what was published by OpenAI for GPT-3. So this, you will notice in the beginning of these runs, we'll spend a lot of time trying to figure out how to bridge that gap. So in October, that's when we first started our training runs. The safest thing to do at the time was to go with kind of the hyperparameters used for the existing language model setups within the NLP groups. This kind of shows some kind of empirical proof for how they could work. The largest model trained up until that point was about 13 billion parameter dense model. So the hope was that these would transfer to the 175 billion scale without any issues. Of course, that didn't really turn out to work. So for the second run, we start increasing weight decay. So we start with 0.01, we increase to 0.1. That didn't really work out. For the next run, we start drastically shifting more towards the GPT-3 settings by setting a gradient norm clipping threshold to 1.0, reducing atom beta 2 from 0.98 to 0.95, and also increasing atom epsilon from 1e-8 to 1e-6, thinking that that could help stabilize the runs. So it turns out none of these settings actually mattered. We realized at the time, afterwards, that there was actually a bug in the code that we used to implement tensor parallelism to scale to 175 billion parameters. We were checking at the time with a smaller scale run and noticed that it couldn't converge. So this is a very obvious lesson. We should have started very small before going to the largest run, but given the time crunch, we kind of short-circuited that, and that came to bite us in the end. So while we were debugging this and we had to revert this code base, causing kind of the training run to go a bit slower, we figured we would at least check the hyperparameter settings and see if they would actually work without the really efficient tensor parallelism code. So here we go back to kind of the old weight decay settings, thinking that that could work fine. And that didn't really, help. We start clipping gradients again, increase the weight decay. And so this is kind of us trying to figure out how these settings interacted with one another at the 1/7 parameter scale. We also increased warm up, thinking that that could help increase the stability of the run. That wasn't enough. So by this point for run 6, we actually fixed our tensor parallel code so that we can train a bit faster. And so we go back to kind of the original settings we had, but still keeping gradient clipping, thinking that that should be pretty safe to include. So that still didn't work. So for run 7, we added weight decay again, we increased warm up again, and we also skipped the last partial batch in case there was an issue with computing the gradients there and causing kind of a little bit of instability with a smaller than normal batch. So we do some more fiddling around, and we also do something, we increase the batch size from 2 million to 4 million. None of these seem to really help. So for the batch size case, since we saw no noticeable improvements, we decided to go with a lower batch size. The hope is that by taking more optimization steps, maybe that will help us converge to a better minimum. So by this point, we think we settle on a few settings that we kind of all compromise on, and we're kind of ready to just launch our actual run. We're telling ourselves that by this point for the 11th run, we should start indexing with decimals. So this is run 11.0. So for this, we settle on a 2 million batch size. We keep our atom states in FP32, so the highest precision. We use tensor parallelism by sharding the model across 8 GPUs. In parallel, we were doing data ablations. I'm not going into detail about that here, but pretty much we're trying to figure out the ideal data composition. And we're also noticing some bugs in kind of when we exported the data set and added a bunch of escape characters. It caused kind of an artificially low loss when the model was just learning to memorize these extra escape characters. So we were trying to make sure that the data set was actually good to go. We also used learned positional embeddings, but we weren't sure whether or not we wanted absolute learned positional embeddings with kind of a Gaussian initialization, similar to GPT-2, or sinusoidal initialization, sort of matching the original transformer implementation. So we kind of just meet in the middle by initializing these positional embeddings with sinusoidal init. Similarly for weight decay, we weren't sure if it's 0.01 or 0.1. That's nice. So we could split the difference and use 0.05. We also use a pretty high learning rate to start. So historically, and kind of the implementation that we had at FAIR, the learning rates were set up usually a lot higher than what was published externally. So for GPT-3, the learning rate was 60-5, I believe. And so we used 3-4, so quite a few factor higher. We also don't apply dropout on embeddings. And we also include normformer. That was some work that came out kind of a couple months earlier from the lab. The thinking there was adding a bunch of layer norms can help stabilize the run. And some other settings as well. So just in the beginning here, this was already starting to look pretty unstable. In the first few hundred steps, that's the first green run you can see at the top there. We thought that maybe this was just because of the learning rate was too high. So the first thing we do is halve the learning rate from 3-4 to 7.5-5 or quarter it. That didn't last very long. So that's the yellow line right here up top. This is our loss curve. And so at this point, we lowered gradient clipping threshold from 2.5 to 1.5. So now we'll clip more frequently, especially in the beginning. And that's the purple line above. So this keeps training for quite some time. For us at this point, getting past a few hundred steps was a blessing. And this is when we hit our first actual hardware issue. We hit an uncorrectable ECC error, so we just restart the run, get rid of the machine. And that's the gray line in the middle there. And then we also noticed that we were validating too frequently. So that was causing kind of a 10% to 20% overhead. And so we reduced the frequency of validation. So while that gives us less visibility into the health of the run, we thought that the speed up would be at least worth it. Then for the next few runs, the gradient norm starts spiking now for the green line. And so we lower clipping threshold again from 1.5 to 1.0. And that we continue training there. So after that point, this is when things start going really, really bad. So this is the zoomed in portion of what we were just looking at. So here you can notice there's a ton of restarts in the middle for us trying to figure out exactly how to get this run back to where it was before. It's hopefully get the loss to continue going down. But we don't make it very far. So The first kind of issue here, we tried remediating this kind of, this instability by skipping batches when the gradient norm was too high. So instead of just clipping it, we thought maybe getting some new data into the mix would help stabilize the run. That didn't work out very well. So we roll back a bit further. And so you see for the next restart, it's at an earlier checkpoint. And here we finally go towards changing some of the other hyperparameters. So increasing weight decay, thinking that can help regularize the updates. We also lower beta 2 so that we're averaging over kind of fewer steps, thinking that maybe we can adapt to the gradients more quickly. And that didn't last very long. So that's the first kind of pink wiggle there. And then for the next bit, we keep the beta 2 sort of at 0.95, but then we go back to try to figure out if weight decay changing or gradient clip changing was something that we needed. So you sort of see this kind of overarching kind of theme of changing a few things at a time and maybe then bisecting. This mostly is motivated by the fact that, each time we do this, it costs a lot of manual overhead, it costs time to validate. So we try to batch a lot of these changes that we think are safe together. Of course, it makes experimentation hard. You can't really disentangle the effect of one versus the other. But this is kind of the expense of, kind of only having one chance to train this model and having to sort of correlate a lot of these hyperparameters together. So that still didn't work out too well for us. The next thing we do now, finally, we go into this lowering the learning rate kind of mode of operation. But that obviously we can't do that indefinitely. But that still doesn't last very long. So that's the orange line here. Now, at this point, we're also watching kind of what was happening in the open source community. The big science effort was starting up and they were trying to train a 100 billion parameter run. And there was this pull request where they mentioned that there's this numerical stability kind of issue potentially with the MHA calculation, the multi-head attention calculation. So specifically, it's a very simple thing. When you're doing multiplication by a factor of n, just split it into multiplication by square root of n twice. And that in some cases for large values of n, especially for large models, could help improve with stability. So we implemented this change and ended up restarting our run. Now we also notice here for the GALU term or the GALU activation, there's this x cubed term, and that could also cause some instabilities for certain layers. So we just swap in ReLU instead, so that we don't have to deal with this x cubed factor. And this trains for a bit longer. This is a pink run, so clearly we can make it past some instabilities here. But the problem was it didn't seem like the run was actually going anywhere, right? It just kind of plateaus. And on the side, we're also doing some other ablations with initialization, thinking that maybe this gradient explosion or vanishing issue, whatever this was that we were dealing with, maybe this was a factor of not initializing properly for such a large model. But none of these ablations actually turned out to be meaningful in any way. So one thing to note here is that when we were training this run back, back in kind of November 2021, even though we were using A100s, which had BFlow 16, we're most familiar with kind of FP16 training with no mixed precision. And so in order to make these runs converge, there was this extra factor that we call the loss scaler that is usually implemented. And the thinking here is that when you're training with FP16, so you don't, and with no mixed precision, so you're not keeping any copy of weights in FP32 or above, we use this loss scaling term to try and preserve small gradient values. So the thinking is, when we haven't overflowed in a while, we'll scale loss up so that you can sort of surface the signal from small gradient values. And then when we start overflowing, we can scale down the loss. And usually what we see is that when this loss scalar crashes to near zero, effectively giving your loss in your gradients to become zero, your model stops updating. So that's also a very unhealthy signal. And when that happens, kind of training stops. So for the pink run here, when things kind of just never converged, you'll see that near the end, the loss scalar was very low. So we weren't really actually getting any kind of meaningful gradients flowing through. So at this point now, we were looking at the clock, and to recap, we know we need at least 33 days of training for a 1.5 billion model on 300 billion tokens and using 992 GPUs. So notice that we changed from 1024 to 992 now. This is after seeing a lot of hardware issues come up and we have to switch in GPUs when GPUs go down. So in order to have minimal downtime, we have to train on a smaller subset of machines and leave a pool idle so that we can swap this in. We also know that we had to benchmark the model before the end of the year. So we really didn't have much time to explore all the hyperparameter settings and try to get things to work. So from looking at all the restarts from the previous lineage of models of experiments, there wasn't any strong signal that these settings would actually work out if we were to keep training with them. So at this point, we decided to do the complete, drastic switch to GPT-3 and Megatron code-based settings, since the two already seem relatively consistent with one another. And there was some evidence that these settings can successfully train models, even though we weren't using exactly the same code base. So specifically here, we updated our weight initialization. Overall, the change was to kind of reduce the standard deviation of all the weights so that effectively you're initializing closer and closer to zero. We also remove a lot of extra layer norms from the norm former setup. So that's now, pretty much exactly mirrors what we think the GPT-3 architecture looks like. We remove embedding scaling. This was a term to kind of scale the embedding to Gaussian with standard deviation of 1, which may be too high. If you notice that the GPT-2 code base, the standard deviation is 0.01 and 0.02 there, so it's still pretty small. And we also go back to Gaussian initialization for the positional embeddings. We did a series of ablations separately and noticed that if we initialize with sinusoidal init for positional embeddings, they weren't actually being updated in any meaningful way. So we might as well just go back to, the Gaussian initialization. Weight decay, we finally go to 0.1 and just stay there. Clipping, gradient clipping, same thing, we stay at 1.0. Atom beta 2s is set to 0.95. And these are all pretty standard now. If you look at a lot of works that's coming out, most folks do use an atom beta 2 of 0.95 with gradient clipping of 1.0. But at the time, it wasn't clear that this was the go-to kind of setup for these larger models. And the learning rate here, to recap, we initially started with a learning rate of 3 - 4 in the previous lineage of runs. And now we just only do 2x the GPT-3 learning rate, which is 1.2 e - 4. And so here for the first 15 restarts, and now you notice that we're indexing with 2 decimal points instead of 1 because we're prepared for up to 100 restarts. And we actually just faced a lot of systems issues. So this is when A100s are just coming online. These are the 80 gig machines. And so we faced a lot of, lost GPU errors, CUDA errors. Sometimes the job would just stop updating, nickel errors, and things would just slow down, et cetera. So while this was not a convergence issue, and we can generally kind of work around it by figuring out which machine is bad, a lot of this tooling didn't exist for us at the time since this was new hardware. We also, of course, we couldn't blame the hardware the whole time. We had some code issues ourselves as well. So when we were doing checkpoint storage, in some cases that wasn't, operating successfully or taking too long given the kind of compute environment we were in. And we also noticed that our loss scaling logic wasn't fully deterministic. So when we actually checkpoint, we lose the state of what the loss scalar was at the time. And this is specifically for the FP16 training once again. And actually, this turned out to be a blessing in disguise. We end up using this kind of non-determinism later on to get through some instabilities as well. So overall, when we see instabilities, these are kind of the 4 metrics we look at. At the top left here, this is the last layer L2 activation norms. And so when that spikes, we also see to the right, the gradient norms for the overall model kind of spike as well. The two generally are quite correlated. Of course, we look at the loss curve of perplexity. And for FP16 training, we also look at the loss scalar, which is, when that crashes to 0, it's kind of when everything else, activation norms, gradient norms spike. So these all kind of are leading indicators of potential divergence, which doesn't necessarily get reflected until a little bit later. So when we hit some instabilities here, the first thing we do is to reduce clipping. Now, so we go back to clipping of 0.3. If you look at this previous plot here, most of the gradient norms are around 0.2. So we decided to be pretty drastic and do a lot of clipping in case, gradient spikes can lead to, kind of a compounding effect. And we have a backup plan of pretty much resetting the atom state in case that was also causing issues and mismatching with the current batch. And sort of repopulating the atom states. We later kind of explored why we would want to do this in a more recent work that came out back in April of this year, where we kind of studied this up to a 546 billion parameter model in order to kind of remediate instabilities. And the next sort of 17 restarts, we go back to the whole hardware issues, ECC errors, lost GPUs, even high like DRAM correctable errors, even though they're not uncorrectable errors, it still can cause issues. with the kind of compute environment we had, there were also some times when the job would just stop updating, and so we had to sort of manually trigger some restarts, and so on. So so this is when we do something quite drastic. The thinking here was that all these instabilities were potentially linked to having our optimizer in a bad state, or maybe just, Atom, in the case that we had it, just for some reason wasn't scaling well. So we decided to test something quite drastic here. It's kind of a bad idea, but we start switching to SGD without momentum to try to get rid of Atom entirely. So first, we try to be clever by approximating SGD. We can do that by pretty much running Atom, but setting beta 1 to 0, and also increasing epsilon to 100, pretty much wiping out the second moment term, and also increasing learning rate by the same factor. In all these runs, it turns out that it actually wasn't working the way we thought it was. The way we were kind of reloading Atom states, the hyperparameters were not being reset. So all these settings weren't, or these experiments didn't actually yield anything meaningful. So we do the honest thing of actually swapping the code entirely, the code path, and we use SGD. But in this implementation of SGD, we also had our own bug of not actually applying weight decay, and we also weren't tuning the learning rate properly. So there were some kind of findings that were coming out or a couple years back where for SGD, you might need a higher learning rate. We weren't really tuning that properly, so we didn't really see any useful signal. So by this point, after all this fiddling and thinking, we probably shouldn't try to be clever anymore, just do the honest thing of lowering the learning rate, we proceed to just lower the learning rate. So the final learning rate curve here looks quite, if you squint, it looks quite like inverse square root like. We go with a kind of linear decay to kind of just, linearly interpolate our way down. The thinking is that you still want to keep learning rate as high as possible without causing instabilities, but we don't exactly know what that value is at the time. And you see there's this little brief moment in the middle there where we increase learning rate. The thinking there was also maybe we were too aggressive in lowering it. Things look too stable for once, and maybe just increasing it back can help us kind of converge faster. That didn't last very long, and we still had to reduce it 2 more times afterwards to keep it training. So overall, when we kind of look at the health of these runs, right, we stare at, this is a tensor board kind of reflecting these metrics. And the main plot up top here is the loss or perplexity curve, and it's very noisy, right? So even if we add smoothing, it's very hard to tell what direction the loss is going. You can vaguely see near the end that maybe things are diverging, but that's only about a few hundred steps, and given the noise, it's still not definitively clear that's the case. But if you look at the other metrics, it's very obvious, right? For gradient norms, so now this is the bottom row here. For gradient norms, you see things, spiking. For your loss scalar, things are crashing, right? Kind of inversely related to gradient norms going up. And similarly for the activation norms, usually we see that decay over the course of training. And when it reverses direction like that and starts increasing, it's kind of a leading indicator that something is going wrong. So in this case specifically, so this is still kind of zoomed out version of what we were looking at earlier. Just by lowering the learning rate and restarting from a checkpoint, you can drastically change the direction of where all of these metrics are going. So the top left here is the loss curve, right? So the green line is restarting with a lower learning rate. Loss keeps going down. It's very clear that there's a directional change there. Similarly for gradient norms, instead of spiking as before, this is the second plot in the middle here on the top row. Instead of spiking, suddenly, it keeps kind of stabilizing and training around like, 0.14. And same thing. So you can sort of see that a lot of metrics can shift just by fiddling with the learning rate. So after 56 days of dealing with all of these issues, hardware issues and these instabilities, we finally end up with our loss curve that looks, something like this over the course of, 300 billion tokens. It's very colorful. There were many, many restarts, even, missing some logs in the middle when our entire cluster went away. But this is, kind of just summarizes how manual this process was to start with before we eventually started automating a lot of this work later on. So I can stop here and take some questions. I also have some more slides for the 66 billion run. I don't know if that's helpful to share. But yeah, I can go into that as well if that's useful for folks to look at. It looks very similar to the 175 billion run. Hello?
OK，大家线上有没有什么问题吗？可以 大概。大家线上如果有什么问题，可以打在评论区处，然后我来和老师进行一个沟通。Actually, Susan, I have a question.
Oh.
Do you think that scaling laws still hold for your model during the research?
Scaling laws in which sense? Like for scaling up model parameter, data size, or just like in general, if scaling laws are useful?
Like for this research specifically.
Yeah, so I mean, in this case, we're mostly focused on kind of the cluster stability and hardware issues and making sure that a lot of the tooling kind of can capture all of this manual kind of operations we were doing to restart the run and whatnot. So it wasn't so much scaling laws as opposed to kind of more the infrastructure side that we needed to build out, and a lot of automation we had to build, say, to detect kind of when things would diverge and how to remediate that. So it's not quite the same thing, but it definitely is valuable to know kind of what the optimal model size and data set size to go for given a certain amount of compute.
Okay, I've gathered two questions online. The first is any idea of training 1,000 billion language model?
Or like what that would look like, a 1 trillion parameter language model?
Yes, the parameters. 1,000
Yeah,
billion.
yeah, 1,000. Yeah. So in that sense, I mean, so right before this work happened, FAIR actually released a 1 trillion parameter mixture of experts model. So that's not a dense model, right? But the parameter count matches kind of what you're asking for. I do think that scaling to a 1 trillion parameter dense model could be quite interesting, but it is also for what we know for how we want to spend compute, right? If we can like feed in enough data, then it might make sense to do. But a lot of the data sets that we're looking at may not be sufficient for that.
Okay. Another question is, why choose to use norm former for scaling to deep models or training stability?
Yeah, I think at the time was that the norm former work sort of showed improved convergence and adding a lot of potential ability to sort of stabilize kind of exploding gradients through the model. That was very exploratory because that was demonstrated at very small scales, and when we started we were trying that out, but we eventually did remove it. So it didn't seem like we wanted to take that chance of seeing if actually norm former was useful at 1.5 billion parameter in case it was actually causing issues.
Okay, what framework do you use in data processing and model training?
So data processing, I mean, at the time there wasn't really a defined framework. This was using existing code that had been, existing kind of data sets that have been processed by other teams at previous works. We started building out kind of a cluster, sort of running kind of Spark jobs, right? It's very standard CPU intensive workloads there. But for us, it was a very ad hoc. Every new data set we brought online, we would have custom logic to process it. For the training side, the code is open source, right? We use Metaseq or under Facebook Research to train this model. It's a fork of FAIRSeq, which was a very common sequence modeling framework that folks are using within the lab. But we specifically forked the code base to focus on decoder only autoaggressive dense transformers, and also to make sure it can scale to the kind of large scale workloads we cared about.
Okay, there's a follow-up question saying that in the process of the IFT period, do we have to use the open source framework of the original author, or we should transfer to a more mature framework like Deep Speed Chat?
IFT, what's the IFT period? I'm not too familiar with that.
I'm not sure though. It's like, should we use the like the open source framework, or like we should transfer to a more mature framework, like deep speed chat?
Okay, yeah, I'm not as familiar with deep speed chat. So I think the question here is like, what is already running on your hardware or your infrastructure and your systems? Because a lot of the details here is not so much which library you use, but actually the integration with your actual compute environment. We had a lot of glue code there, like what, where you load data from, how you're doing like your checkpoint storage. That is most of the complexity in adapting any code base. So if you are able to sort of swap out, these frameworks, that's great. But a lot of the time we spend quite a bit of overhead in making sure this code just can work in any kind of compute environment.
Okay. Another question is, what do you think is the main cause of result difference between OPT and the Bloom model? The other model?
Oh, yeah. Yeah, my understanding was that Bloom is very multilingual. And so if you were to focus on kind of English only results, I think Bloom just did not see enough data for English only. So if you were to just like look at English NLP benchmarks, right, you'll see a delta. And I don't think that's really meaningful given just the different training set that was used for Bloom.
Okay. Oh, there's a question saying that is OPT able to surpass the performance of Llama model? Actually, the author of Llama model came to our community to give a speech just a few weeks ago.
Yeah, if you added more data for OPT models, I mean, there's nothing fundamentally that different between the two. And I don't think the architecture differences are meaningful at all. We just didn't have enough data, right? So we had to train this model, in a very defined, finite amount of time. And only 180 billion tokens were available to us at the time. So if we 10x that data set, I don't think there's going to be any issues with benchmarks. And also, this is also with a huge caveat of the benchmarks are English only, and we did not filter our corpus for that either. We were trying to see if there was multilingual behavior that we can capture with very little data.
Any latest progress in your team related to enhance smaller LLM reasoning ability, or we still cannot understand reasoning?
Yes, so yeah, I can't really comment on that either. That's a lot of internal work going on.
Okay. How would you compare OPT and Llama model? Do you have any future plans to improve OPT? That's a pretty general question.
Yeah. So I mean, like I mentioned before, it's the main difference is data set, right? So I mean, we also worked on the data set for Llama, and if you actually look at the details of the Llama paper, they do mention that. So the main thing that we're focused on, and you also can see from the kind of atom instability work, like we are scaling to larger models with the 546 billion parameter run. In that regard, if you feed it as much data or more than Llama, we can probably see a difference there.
Okay. Do you use any extrapolation techniques in OPT model training? If yes, do you think it's useful in improving context length?
Oh, extrapolation techniques. Well, yeah. Is that like kind of taking a pre-trained model and then increase context and then sort of fine-tuning on a longer context window? Or I'm not quite sure what extrapolation means. It could mean something else too.
I'm sorry, I'm not sure about the details. I think do you use any extrapolation techniques in OPT model training, like how to read this? Alibi, ALIBI.
No, I see. Yeah, alibi. We did not use alibi. So we used learned absolute positional embeddings for that without any alibi.
Okay.
Yeah.
Do we have more like general questions instead of those technical details? Actually, as a member of BAI, I have a question concerning the research mechanism. I wonder what's it like working in a research team in Meta AI, and how do you propose subject to research, or is it like very flexible, the research mechanism, I think?
Oh, like how to choose a research direction and how much flexibility we have within Meta for that?
I mean, like, what's it like doing
More
research in Meta AI lab?
Yeah, so it's changed it just in the short time I've been there. There is a subset of FAIR that is very open-ended research. You kind of have a lot of flexibility in where you choose to take things, and there's like a shared pool of compute that you can use. And then there's a portion of the lab that is also very focused on specific projects, right? Kind of one of the examples is a lot of the Blender bot work, is focused by a very specific team. Similarly with recent releases like Cicero back in November, where a specific team worked on just solving kind of the diplomacy game with a combination of RL and language modeling. So there's also some focused efforts there where you can kind of form these very specific project teams and just go towards that. But that's also sort of slowly shifting over as there's a lot more focus on generative AI these days. And so more resources are going into a lot of generative AI research as well.
Okay. There's one more technical question. Do we have any extra optimizer except Adam to speed up or stabilize?
Yeah, there's been a lot of efforts in trying this. I still have yet to see much that can scale well past, a few billion parameters where the gains are actually meaningful. I'm sure there is still work to be done in this space to, sort of improve this for large scale training, but I just personally haven't been able to get, many to work above, say, like 30 billion parameters.
Okay. How do Meta think of LoRa for fine-tuning LLMs?
It is definitely useful. There's many folks exploring applying LoRa to fine-tune.
Okay. What's the purpose of training OPT? Where do you think the emergence ability of LLM come from? Actually, I want to ask about that too. Like, what do you think about the emergence ability of the model?
Yeah, so you have to remember the context here back in August and September 2021, right? Back when nobody was releasing large models. There was this kind of aura of it is risky, that especially coming out of GPT-2 when they did a stage release just for a 1 billion parameter model. So a lot of focus for OPT was a combination of testing out new hardware and making sure we can actually sort of set ourselves up for more scaling efforts going forward, and sort of make things like Llama be almost trivial to work on. And then as well as sort of being able to open source this so that people can start prototyping at larger scales and making these larger models more inference efficient and so on. So, there's a lineage of work that came out of that, right? Sparse GPT, FluxGen, et cetera. These are all kind of different works testing whether or not you can make these large models kind of have the same performance as they were with full precision and whatnot, but then say, lower precision or more sparse or whatnot, and seeing if that can actually run on commodity hardware. So the release of OPT, especially with all the smaller models, 125 million parameters up to 66 billion, and then also obviously the 175 billion parameter, is to sort of enable people to study scaling laws, right? Seeing if we can actually scale up and transfer kind of methodologies from a smaller scale to a larger scale, if it'll work just as well. And also obviously sort of showcase the kind of complexity of actually operating at the scale on new hardware, right? By releasing a logbook, showing kind of the excruciating detail it takes to do this for the first time on new compute environments, and also releasing the code base as it was for training these models, which I think Megatron Turing in theory sort of did, but it was very hard to get that really running anywhere. And it wasn't clear if that was exactly the code base that was used to train their largest models, whereas we literally just open source the one code base that we use. So this is one of those things where you see a lot of papers publish details about training and whatnot. A lot of folks, it's not intentional if they left out details. It's just there's so many implementation details included in code that may not be captured in papers. And we just wanted to make sure that everything was out there. Oh, and then, I think there was another question, emergence, right? So that's the other part where I think that's the bitter lesson of scale, no matter what, as you say, if you have, unbounded data. If you have the compute to train a much larger model on the same amount of data as you would on a smaller model, for capabilities to emerge or whatever that, capabilities looks like, purely just from modeling, having more capacity to model any kind of underlying pattern in the data, you will see more quote unquote emergence in that sense. But a lot of that is also, I think, contingent on what you're using to measure and whether or not that, emergence is actually some kind of hockey stick or kind of a smooth curve. So I think the ruler by which we're kind of claiming there's emergence is also kind of a ill-defined term.
Okay. The future technical path of large language models, do you think it's a decoder only, or it's rather encoder decoder?
This is tricky since from a lot of kind of discussions with researchers in the space, if you were to kind of fiddle with the number of encoding layers and decoder layers, in the limit, you sort of see that if you reduce the number of encoding layers, you actually get better performance in certain use in the generative case. Now, of course, I think that's subject to what you mean by performance. If you're trying to like adapt this model and fine tune it and to it, sort of shift the domain distribution of the pre-trained model to some new data set distribution, maybe you do need an encoder to help with that sort of tunability of the model, which is very different than, say, training the most capable model. So in the final use case here, it's also very unclear which, if there's a material difference in architecture that results in better results as a function of kind of the data that you have. From all of our experimentation, right, for ease of scalability, decoder only definitely, scales much better on the hardware that we have, but I do see a world in which you can probably make encoder decoder work just as well. But I think in that sense, scales matters more than, say, the specific details of architecture here.
So decoder only and encoder decoder, they excel in different specific tasks, right?
From what I've seen so far, yes. And maybe that's just completely, that's also arbitrary because we've only have very few tasks that we look at here too.
Okay. Yes, we have a general question. Any experience to share when developing and managing such a huge project? For example, how to set benchmarks and deadlines?
Yeah, so overall, there was this kind of trade-off, right, that you see between like research risks that you can take where, trying out new things for the first time at scale versus kind of engineering risks that you can take in like just pretty much purely executing on what is already out there, right, and not actually trying novel things. So there's that trade-off of like, if given some amount of compute that you have to produce a model at the end, whatever that looks like, right, you probably don't have the luxury of trying a lot of novel new architectures, new optimizers and whatnot. And most of the complexity comes in the form of actual engineering execution and getting things to run on new hardware. So I would say, right, even in the kind of haphazard way it looks like when we're trying to changing these hyperparameter settings, we're also doing like we're only fiddling with a very small number of variables. Now, in theory, that can like combinatorial explosion can be, somewhat, unbounded, but still, right, we're not taking too many risks there. And that's mostly because each time we restart, and these tests are not cheap to run. We're still aiming towards getting kind of the run back on track as soon as possible. So I would say, in that sense, like a lot of this work comes down to minimizing kind of unknowns and trying our best to get to the trained model as quickly as possible. And it might look a little bit haphazard, but that's mostly because we have a very bounded amount of compute time to spend.
Okay. I can see the time is ticking, so let's take 3 more questions. The first is, we should make LLMs remember the knowledge in the pre-training phase. Does this mean we can't use dropout in the pre-training phase?
I think the two are pretty decoupled. Dropout was introduced as this like form of regularization, and it helps kind of break up correlations in the model so that maybe you can like learn a more robust representation. Anecdotally, so we sort of see, right, even from Palm, the 540 billion parameter model that Google trained, they start removing dropout, and it seems like there was no difference. I believe Llama did as well. I have to double check if that was true. But even for our 546 billion run, we took dropout out, and we didn't really see a difference. So it's one of those things where I think it might make a significant difference at smaller scales, similar to like There was a primer paper that came out a couple of years ago that showed that ReLU squared is a great activation function, made things train a lot faster. But that's one of those things where at scale, with numerical instability issues, that just wasn't feasible for us to actually apply. So things that look promising at smaller scales may not extrapolate to larger scales. So yeah, I would say like the two, for dropout in this case, kind of unrelated to, I forgot what the other thing was, but yeah.
Okay. What are the main challenges and limitations faced when applying autoregressive models such as GPT and Llama model to African languages?
Oh, I don't have any experience in African languages, unfortunately, so I can't comment on this at all.
Okay. What do you think of generative models versus joint embedding architectures mentioned by Yan LeQueen?
Oh, yeah, I don't think I can comment on this either. More of an engineer here than speculating on research direction.
Okay, so I think it's about time, and I really thank you again, Susan, for giving us this presentation. And next time, I hope you can really join offline for our conference.
Yeah, I would love to. Thanks so much for having me. Yeah, this is great. Thank you so much. Yeah.
Yes. So thank you again.
Yeah.
结束。